We're moving more into the solving aspect of the square root function, and just a reminder that what we could do is we can actually solve some of these square root by using the store feature in our calculator to check our answer. And I know some people, well, maybe you would just do this problem a little bit differently, but anyway, all you have to do to solve a square root problem is to undo it through squaring. Sometimes what I'll have students do is remind them, and I don't know if you're well aware with this, that the square root is the same thing as x to the 1/2 power, but we can undo to the 1/2 power by squaring it, so it's also 7 squared, because a power to a power, you multiply those exponents, and 1/2 times 2 is 1, which is why we're left with just x equals 49. I think I'll save you some time and just, you can trust me that the square root of 49 is 7. So notice with the next one that the order in which you do this matters, because you don't want to do add 3 first. You want to start by squaring both sides. And same logic though, the square root and the square cancel each other out, so you're just left with x minus 3 on the left side, and on the right side 5 squared is 25. Now you want to solve this by adding the 3 over, and x equals 28. So this might be a good time to remind you of the store feature in your calculator. Just getting out my calculator, I'm going to hit 28, store in for x, and then I can hit alpha square root x minus 3, and I got 5, which is what I was supposed to get, because I was substituting 28 in for x. Minus 3 is 25, square root of 25 is 5. And then same thing goes for that last one over there. You start by squaring both sides, so you're left now with 2x minus 1 is equal to 16. Add the 1 over, and I like to leave my answer as 17 halves. I'd be fine if somebody changed it to 8.5, but 17 halves is a good enough answer. Now the next bit is more complicated, and I use the phrase that you want to isolate the square root. Sometimes I use the phrase radical, isolate the radical, because that's what the square root symbol is called. So if you notice, it's just 3 times the square root of x and then minus 4. So the order in which you do this is very important, that you want the radical by itself first. So you start by adding the 4 over, you get 24, and then you divide by that 3, so then you're just left with the square root of x is equal to 8. And now you square both sides. So notice how different this problem is. That you have to go in this order. So you might have thought that wasn't too bad, but stick with me with the next one. It's a little bit more complicated. You do start the same process, subtract the 7 over, but you do not mess with that 5, because the 5 is under the radical, and just like I did over there, I got to divide the 2 next, so it's just root x plus 5, and that's what I mean by isolate the radical. Get the radical by itself. That's what isolate means. And now you can square both sides. The square root and the square cancel each other out, so you're left with x plus 5 is equal to 9, and then subtract the 5 over. The very last thing to do in this problem is to subtract. So you get x equals 4. Again, I'm going to just have you trust me. If we were in class, I might ask a few more probing questions to make sure that you're good, because the next one's really the same work. Notice that I'm undoing the addition or subtraction first. So that's 40. Then divide by 5. So we're left with the root of 3x minus 2 equals 8. Then you can square both sides. So 3x minus 2 is what you're left with. The square root cancels out with the square, is equal to 64. Add 2 over, and then when you divide by 3, you get 22. There you go. So remember, at any point you can pause this video or rewind, and you can rewatch it and do things like that. So with the next one, it's not any more difficult. It's the same thing. You got to get that radical by itself first. So divide that 3 over. So you're left with the square root of x plus 2 is equal to 5. So then when you square both sides to get x over 2 by itself is equal to 25. So then you can multiply that 2 over. It's the only thing that's different to get x equals 50. Option 3. So again, pause the video, try some of these on your own, re-watch it, see if you can get it. So now what we're going to do is practice with our graphing calculator, but then I'm going to show you algebraically what happens here. So using a graphing calculator, let's see, unless we've already done this, maybe you remember that this function that I'll do, this one in blue, I was going to do it in blue, is it shifted left 3, so right here, and then it opens up and to the right. 1, 2, 3, 1, 2, 3, 4, 5, and I think that's enough points. But with a graphing calculator, if you're not quite familiar with this yet, you could go to y equals on your graphing calculator, hit the square root key, x plus 3. If you go to your graph, whoops, forgot I zoomed in somewhere. You can see that, but you can also go to your table, second graph, and you can see some of the ordered pairs I put on there. -3, 0, -2, 1, 1, 2, so on and so forth. Let me do that other one in this purpley-ish color. Y equals x plus 1. Remember the y-intercept is 1, and then its slope is up 1, right 1. And then I think from there it's pretty clear what the point of intersection is. That it's the ordered pair 1, 2. So what does that mean? When x equals 1, I just jotted down right here, both y values equal 2. And that is true if you look at both of those. So how could we solve that algebraically? Well, if I go back to the original problem, I can set them equal to each other. Why? Because they have to have the same y value, so everything else must be equal as well. So what's different on this problem is when you square both sides, the left side, the square root and the square cancel each other out. But on the right side, remember you have to FOIL that out. That means the same thing as x plus 1 times x plus 1, which we spent all of Unit 3 talking about. It's x squared plus 2x plus 1. And then we had the method of solving this is by setting it equal to 0. Well, we can do that by subtracting 1x over. So 2x minus 1x is 1x. And then 1 minus 3 is -2. And when we factor this, x plus 2, x minus 1, you may remember that our solutions were the opposite. Let me write it down over here. That x could equal -2 or +1. But if you look at our problem, -2 didn't work. Why didn't -2 work? Well, if we went back to check our work and we plugged in -2 in for x right here, -2 plus 3 is 1, and the square root of 1 is 1. But if I were to plug in -2 in for this x, -2 plus 1 is -1, and what we get, let me write it out, for x equals -2, we get y equals 1 and y equals -1. Are those the same y values? No. So the whole thing is, it goes back to this statement right here. I'm putting boxing it in red, is because when you square a number, it takes any negative number and makes them positive. So we end up getting negative numbers equal to positive numbers, which is false. We call these extraneous solutions. They are called extraneous because algebraically they work, but when we check it when the original equation, they don't work. The only correct answer, let me write it down, only correct was x equals 1. And when we went back to the original problem, it still worked. We got y equals 2 on it. So that's where we get this phrase where you want to check for extraneous solutions. We want to make sure our work is correct. So that's what we're doing on these last two problems. You start by squaring both sides. So when I do that, just a reminder, the square root and the square cancel. On the right side, make sure you FOIL that. If you're not sure what I'm talking about, pause the video and remind yourself how to do x minus 3 times x minus 3, because that's what the right side it really is. And then from here, I would subtract 2x over. I would add 3 over. And then factors of 12 that add to be negative 8 would be negative 6 and negative 2. So we're looking at x minus 6, x minus 2. So what I'm saying is x could be positive 6 or x could be positive 2. And now we need to check for extraneous solutions. So if I plug in these values, let's plug in 6 first. 2 times 6 is 12, minus 3 is 9, square root of 9 is 3. I'll just jot it down right here. And 6 minus 3 is 3. Yeah, that was good. That was correct. Let's try x equals 2. 2 times 2 is 4, minus 3 is 1, the square root of 1 is 1. But on this side, 2 minus 3 is negative 1. Oh no, that is not correct. X equals 2 is the extraneous solution. So the only correct answer is x equals 6. All right. So the next one's a little bit more complicated. Because the square root is not isolated, you want to add that 2 over first. And now everything else is the same. Maybe I'll do this in green just because I feel like it. So again, if at any point I'm going too fast, you can pause the video, think about what it means to be 2x plus 2 times 2x plus 2. And on the right side, the square root and the square would cancel. Let's get it equal to 0. So we're looking at 4x squared. Let's see, minus 1x over, minus 6 over. And then you can do that AC method. Factors of negative 8 that add to be 7 would be 8 minus 1. But don't forget to divide by your 4. So we're looking at the factors of x plus 2 and then 4x minus 1. So x could be negative 2 or x could be positive 1/4, and then check our work. Because 2 times negative 2, let me do this in black. 2 times negative 2 is negative 4. Does that equal negative 2 plus 6? What's that? It's 4. Square root of 4 is 2. 2 minus 2 is 0. Oh, that was definitely wrong. Let's try 1/4 now. 1/4 of 2 is 1/2. Yikes. I might need a calculator for this one. Square root of 1/4 plus 6, arrow over to get out of the square root, minus 2. Let's see. Yep, looks like it's 1/2. Yes, 1/2 equaled 1/2, so that was the correct answer. Negative 2 is extraneous and 1/4 was correct. And we should be ready for your homework.